नमस्ते सदा वत्सले मातृभूमि. Hello friends. Namaste all of you. Namaste everyone. And myself Hsc S.S.Takalkar, of course, was friendly teacher. Dear friend, I wish you have a pleasant day today. I mean, if you lose your ego, the atmosphere surrounding of you becomes very happy and pleasant. Okay, dear friends, as you know, the matter is made up of, or it has some characteristics, and it is made up of different particles, or it has space and mass. Further, according to its state of existence, it can be classified as solid, liquid, gas. These are three main types of the states. However, in sun-like stars above 10⁷ degree Kelvin or modest temperature, the plasma state can be existed, or very low temperature, very low temperature, absolute zero temperature, super condensed state can be existed, where all the entities behave similar. So these are very rare. Okay. So we are not going to study about these states, but as you know that solid, okay, can be converted into the liquid or can be converted into the gas. And these are the reversible processes, physical transformations. At its melting point, where pressure is 1 atm, then the temperature, so what is called as a melting point, okay, can be converted into liquid, or the liquid where it is called as a boiling point can be converted into the vapor state. This is the opposite processes known as condensation, okay, or this is the freezing process, and freezing point. Okay, we are going to study the solid state. What is it? How we define it? How the solids are defined? Firstly, the constituent particles are very close space. Okay. And binding forces between the particles are quite stronger one with compared to the liquid and gaseous states. Here the space between particles is lower, and therefore they not compressible. Okay. Actually, these solids further can be classified as crystalline solids and amorphous one. In practical, this can be, it appears hard, it is said to be a crystalline, and the powder of this amorphous substances, it feels or appears soft, it is said to be amorphous. They are different. Generally, crystalline substances are soluble and polar one and dissolve in all the salts in water. Okay. So here, consider the crystalline one and amorphous solids. Very important point of this is that in a case of crystalline solids, the particles, they are arranged well. Okay, regular arrangement is there. So here there is a long term, there is there is long-term arrangement of particles. So it forms unit cell, unit cells. These are the smallest but definite building units. Okay, so it gives a structure of that crystal lattice. So these are the smallest fundamental building unit, but having a definite arrangement. Smallest one. Okay, and because of this, they have definite binding process, and therefore they have definite heat of fusion, enthalpy change of the fusion. So they melt at a particular and sharp melting point. Okay, that is, they have a sharp melting point. Okay, so here in this case, because of this, one thing is very important about this: they have clear. They shows clear or clean. Clear edges. When they break, then the edges for that particular piece is very sharp, and clear edge is very sharp. Okay. Whereas in the case of amorphous, one can also written here amorphous. The very important and the point for this is that amorphous, there is a random, okay, short random arrangement. Okay. And again, there are not formation of unit cells because there is no regular and definite arrangement. Here, no definite heat of fusion. It is right. Okay. Or no definite sharp melting point. And again, no clear. Yes. A very important point we are going to study here, that is, in case of crystalline, they are anisotropic in whereas in case of amorphous, they are set within isotropic. What is it mean? Anisotropic. Okay. Dear friends, if you consider some arrangement, so there is some regular arrangement, and one layer, second layer is stacking over upon the first layer, or the next layer can be stacked upon this. This way, number of layers going to stack one over another and forming a definite unit cell. Okay, if you consider some ionic compound, there are therefore some cations and anions, they are arranged in a regular fashion. Okay, like this. So there is a definite distance at which they are arranged. Okay, so these are suppose anions, and as you know, anions have larger in size than ions. Okay, size because the nuclear force per we need one electron decreases here. Number of electrons increases, the nuclear charge remains same, and therefore the attraction decreases, and therefore electron goes away. Anions are larger in size. So this is suppose anions taken main size, and in a space suppose there is cations smaller size. Okay, these are the suppose cations. So in this way, if you draw a crystal lattice points like this, then this is about the crystalline substance. And about the here the particles, they are arranged, random arrangement is there. Okay, random arrangement is there. There is no specific arrangement. Okay, the particles randomly arranged, and therefore if certain properties, for example dipole moment, if you measure or some refractive index, these properties of any substances depends upon that particular substance nature. Now, if you consider the direction of the measurement like this, okay, so here is a anion, cation, anion, cation, anion, cation, anion. Okay, so in this way one can observe that the alternate. If you consider this direction, so there is all the anions in this part, or all cations in this part. So here, as the direction changes, then what happens? Its topic is changes, and the property going to change. So these properties, in the case of crystalline substances, depends upon the direction of measurement, and therefore they are called as anisotropic. That means the properties are not similar. Okay, certain properties. For example, refractive indexes or dipole moment. Okay, dipole moment, etc. Okay. Are changes according to change in direction of measurement. They are called as, therefore, crystalline substances are said to be of anisotropic in nature. So what is anisotropy? That is, this is the property with which the certain physical properties are changes according to the direction of. Okay. So this is the direction, and there is a change in the properties. But if you consider here, there is a random arrangement. So anywhere, generally, almost the environment or this, according to the direction, the arrangement is not going to change. And therefore, if you measure these properties with changing the direction, this or any direction, there is no change. The values obtained are same. So these are said to be isotropic in nature. Okay. So amorphous substances are isotropic in nature. For example, of this are examples different. For example, polonium metal or some diamond. Okay. Sodium chloride or some cesium chloride or sodium chloride or some urzite structure. We are going to study these two structures here: blend structure, zinc blend, or urzite structure. It is one of the harmonic initials and having a crystalline in nature importance. chloride structure and are Na2 anti-chloride. This is called as anti-chloride. This is a chloride structure. Okay, because these are in your state. Cesium chloride, sodium chloride, the unit cell of zinc sulfide. There are two such unit cells, the chloride structure and anti-chloride structures. We are going to study all these unit cell. There is a regular arrangement, crystalline sequences. And if you consider some glass or some rubber or some plastic, etc. So they have no sharp melting points. Okay. There is a wide range with which they can melt. Okay. So here this property is very important. Dear friends, if you consider the structural arrangement or crystal of the constituent particles, if, for example, if you consider the sodium, say chloride, and some magnesium oxide. So it is found that their structural arrangement are same. They are different substances. Okay. Here, say to be a different substances having same structural arrangement. Okay. Same structural arrangement. They are called as the isotopes or isomorphs. Okay, isomorphs. For example, because here sodium and chlorine, they are 1:1. Magnesium to oxygen ratio, atomic ratio or particle ratio is 1:1. Or some suppose iron, chloride and chromium oxide. So here the iron and oxygen particle ratio, iron is 2:3. Okay. So here if you also consider sodium nitrate and say calcium carbonate. Okay. So here 1:2 carbon is added 1:3. Here also 1 nitrogen is 1 in the ratio, number ratio and 3. So here there are the different examples of different substances having the same structural arrangement. They are called as isomorphs. Okay. And however, it is polymorphs. Okay. Or this is also known as allotropes. Okay. Allotropes. These are the same substance having different arrangement. Of the particles. Or here the crystalline structures are different. That is crystalline structures are different. Okay. What it means? For example, diamond, graphite, there is. Okay. These are the allotropes of carbon. Okay. This is the allotropes of carbon. Okay. Carbon. Diamond. So this is a very important substance, diamond, where each carbon is in sp3 hybridization. So here, if you consider the sp3 hybridization, that means all valencies, 4 valencies of carbon are fulfilled. Okay, satisfied. Okay, and there is a network of carbon covalent bonds in sp3. Okay, therefore there is no any Hsc electron. Okay, all electrons are engaged in the bond formation. Okay, no free electron, or the electron, they are engaged in all the covalent bonds. Okay, and therefore it is non-conducting. And there is a carbon-carbon network. So it gives, okay, therefore what happens? Therefore also it is very hard, having also melting point is very high, about 3500 degrees Celsius. Okay, and as you know, the purity of diamond is expressed in carat. Okay, carat purity expressed in carat. Okay. So carat is 200 milligrams. Okay, here. So in the case of diamond, all the carbons, suppose this is a carbon, and tetrahedral. So this is the one bond. This is the another. So this is the one carbon, and there are here. So here, suppose this is the carbon, tetrahedrally bounded to all other carbons, like this, and having the angle carbon 109.87 minutes. Okay. So here, in this case, if you consider the any carbon like this, okay. So here, suppose this is the one of the carbon, then this can be here above the plate. So this is the, here is again one more carbon there, this in one plate. Okay. Similarly, in this way, there will be some different tetrahedral carbon. Each carbon is in sp3 hybridization, and there are no such a free electrons, and therefore there is a, it is non-conducting also. The bond length of carbon is up to 154 picojoule or 1.54 angstrom also. Okay. Now, in this case, the diamond is very strong, and it is because of the network of carbon-carbon covalent bonds. They are in sp3 hybridizations are there, and there are no free electrons or mobile electrons. valency is satisfied. Okay. Now, if you consider the more next important electrodes, that is the graphite. Okay. Graphite. What is that graphite? Graphite. This is the one more electrodes of carbon, okay, or polymers of the carbon, because carbon has number of polymers. So here graphite is the carbon atoms in graphites are in sp2 hybridization. Okay, sp2 hybridization. What it means? That means there is pi bonds. Okay, and pi electrons are delocalized between 6 member rings or 6 member planar rings. Okay. So here, if you consider what it means, suppose this is a one plate, and in this way it forms like this. Okay. So here suppose a carbon. Now there is a one pi bonds, and pi electrons is a overlapping, lateral overlapping. Okay. So here there are 3 sigma bonds. Okay. There are 3 sigma and 1 pi. Okay. Now if you consider this is the one plane. Okay. One can continue here. Similarly, here also one can represent here another. So what happens here? Okay. So in this way one can plot. Okay. Now the pi electrons, they are delocalized, and they are forms of bonds delocalized between 2 layers. These are the pi electrons of carbon in sp2 are delocalized, and because of this there is the structure is flexible one. Okay, flexible, and therefore so what happens here? This distance is about 340 km in this layer. Okay. Or this one angle carbon bond length. Okay. Is less, and this 141 km. Or this can be 1.41 angstrom. Okay. That means, as you know, angstrom is a centimeter, and P is square. Okay. Meter. Okay. So here, in this case, one can write here. So here is one way is 5 plus. Because of this delocalization delocalized pi electrons because of the carbon is in sp2 where the pi electrons are there in between, and therefore graphite is conducting conduct to the electricity. So here, and because of this arrangement, if some pressure or stress applied, two layers can be slide, and therefore it is graphite is lubricant. Is lubricant. Whereas diamond is very hard and heavy. Okay, but because of this arrangement and this carbon nature, which is in sp2 hybridization, there are two electrons. The electrons are free for the conduction, and again these two layers are binded, or there are the pi electrons which are delocalized, and therefore these two layers can slide over each other. So in this case, if you consider the conductivity of graphite, it is used in as a rod, carbon rods, graphite rods, in the case of different shapes. Okay. Dear friends, let us consider the next electrodes. Those are the polarities. What is mean by polarities? One of the important polarities. E and E. What it means? This means it is, or these are alkanes. That means carbon is in sp2 hybridization. That is, there are three sigma bonds and one pi bond. So pi electrons are delocalized. As you know, pi electrons are delocalized, and polarities are therefore conduct. Generally, these polarities are obtained in electric arc. Or from use. So from the carbon, this electrode can be obtained at elevated temperature using the electric arc. So here the soot is obtained, and in this case the polarities are prepared. Generally, these polarities are soluble in some organic solvents. Okay. Generally, the examples of these are polarities. These are very important. Example is the Buckminster polarity. Okay. Or buckboard, also known as buckboard. Or this is nothing but the carbon 60 carbon atoms they forms a football-like structure. Football-like structure. How the football is made? As you know, there are 20 hexagons and 12 pentagons. Okay, you can observe the football. So here the saucer structure. Okay, this Buckminster is actually, he is the US architecture. Okay, architecture, and he built a building having this saucer structure, football-like structure, dome-shaped building, and therefore the name is given. Okay, for this molecule carbon 16. Looking at the football, where there are 20 hexagons and 12 pentagons, and all carbons, of course, all carbons. How many? 60 carbons. 60 carbons are in sp2 hybridization. And therefore it is conducting or superconducting also, and it solves for example potassium salt of this Buckminster is superconducting. Because as you know, these polarities, there is a long chain of the carbons. Okay, there is, or it contains different examples having a carbon from, suppose, carbon 28, carbon 50, 50, carbon 60, or carbon 84, carbon 340, etc. Okay, so this is the important example we are going to study here. Carbon 60 is one of the conducting, very important superconducting salts can be prepared, and this is soluble. Carbon 60 is soluble in organic solvents like benzene or some toluene. Okay, toluene. And giving a purple solution also. Okay, so here the importance of these polarities are, they are first alkenes. Again, they are conducting because all the carbon valencies are not satisfied. There is a pi electrons which are always delocalized. Okay, so here, as you know, carbon 60 is one of the example of polarities. So secondly, okay, this is the one, carbon 60. Okay, this is the one. Again, we are going to study here second example. This is a football-like structure. Okay, so spherical structure. But here second is a tube, nanotube. Polarities. What it means? Nanotube. The nanotube polarities. So it forms a tube or cylindrical shape. And the length from few micrometer to some millimeter. Okay, long tubes, cylindrical. Okay, all these are the, of course, carbon is all carbons. is sp2 hybridization. Therefore, there are 5 electrons are there. 5 electrons, and these are the localizer. Okay, are delocalized, and it gives conducting. Okay, all these are conducting. Electrical. So here, these nanotubes, very important property of these nanotube fluorines are very having a high tensile strength. Okay, therefore they are used instead for conducting cables. Because they are conducting, so the conductivity to the electricity, as well as they have a very high tensile strength. Okay. So here, all these are the sp2 hybridizations are there, and therefore the delocalized pi electrons giving the conductivity to the nanotubes polarities. So here they are also known as Bucky tubes. Also known as Bucky tubes. These are the Bucky ball. These are the Bucky tubes. Okay. Now the next important examples we are going to study, that is the graphene. What are the graphenes? These are a planar structure. Polarities. It is honeycomb like. Okay, and of course these are also planar polarities. Okay, and about carbon 500 in number. Example. Okay, all these are the aromatic compounds. In nature. Therefore, there are the pi electrons are delocalized. So here they are responsible for superconducting. Okay, so carbon has a tendency to form carbon-carbon linkages. It may be a pi bonds or it may be sigma bonds, and therefore there are number of alcohols of carbons are found. So one can differentiate the diamond versus graphite reagents. In this case, there is a sp3 hybridization of the carbons, no free electrons, there is no localized electrons, they are hard, okay, and generally they are used in cutting tools, okay, they are used in cutting tools or drilling machine, or some borewell jet. Okay. Whereas these are the conducting one, they are soluble also. Soluble, this is insoluble. This is a hard, these are the softs. These are conducting, these are non-conducting. Okay. The melting point of this diamond, there is a very strong network. Okay. And therefore it is a high melting point also. Okay. So here, consider the H point, that is the solids oppose crystalline solids. Okay, crystalline solids, how they are arranged in practice, how the crystal, big crystal is formed. Okay, so here, according to the constituent of in a crystalline classification of oppose crystalline solids. Okay, here first very important, that is the molecular solids. First, then ionic, yeah. Ionic solids, metallic, and this is a covalent solids. So there are four types of the crystalline solids can be classified. So what are the repeating units? First point, repeating unit. What are repeating? In the case of molecular solids, the molecules are repeating solids. In the case of ionic solids, there are the positive and negatively charged ions. They are repeated throughout the crystal lattice in a particular fashion. In metallic solids, the atoms are the repeating units, and in covalent, they are also known as a game, or also known as a network. Okay, solids. Okay, also known as. So there is non-metal or non-metal atoms. Okay, or atoms of non-metals. So these are the repeating. Now, how these constituents they are binded? So what are the binding poles? Binding poles. In the case of molecules, again, they are molecular solids. They can be classified as this is a polar molecular solids. Second, non-polar, and third, hydrogen bonded molecular solids. Hydrogen bonded. Okay, and because of this, one can write here, in the case of polar, the dipole interaction is there. Dipole, you studied last time, interaction. interaction. What means, suppose there is a example. What are the dipole interactions, etc. Now you consider HCl bond, covalent bonds, but there is some negative because this is electronegative, electropositive, and this can be also be located as this. So here minus and plus dipoles, electric dipoles are there because of the difference between the polarity. Okay, and it can be explained on the basis of Hazan's rule during the 11th standard. Okay, so here because of this dipole interactions, the molecules are forms a solution. Of course, and very low temperature and high pressure. Okay, so it is formed here. So here this is important. At room temperature these are gases, but when the pressure is applied or temperature minimizes, decreases, okay, at very low temperature they can be converted into the crystalline forms. They are molecular solids, and of course these are very weak, therefore weak forces, therefore they have low melting points. Okay, and all these are also non-conducting. Conducting. Okay, there are no three ions. Okay, in the case of non-polar there are weak van der Waals forces. Okay, forces, or they are also known as London forces. Okay, dispersion forces. Okay, these are the dispersion forces. So here, in case of hydrogen bonds, of course there is a hydrogen bond. It may be a intra-hydrogen bond is there, or inter-hydrogen bond. Maybe. Okay. For example, if you consider glycol. Okay. So here the hydrogen bonds can be formed. Okay. And of course, number of examples are there. Here the bonding between, what are the hydrogen bonds? That is the bonds between hydrogen and electronegative atoms like, okay, electronegative atoms like the chlorine or some oxygen or some nitrogen or some sulfur. These are the electronegative atoms. So hydrogen is must there, and it may be bonded intra or inter hydrogen bonding with the electronegative atoms like chlorine, oxygen, nitrogen, sulfur. Okay, so number of examples are there. Suppose HF. Okay, or some amines compounds, organic because nitrogen is there. Okay, so chlorine is electrons is there, or carboxylic acids, or some alcohols. Okay, so it forms the some hydrogen bonds. Now, non-polar case, non-polar molecular solids, the molecules, they are non-polar molecules. Okay, and these non-polar molecules, okay, here with van der Waals forces are there, and here there are non-polar molecules. Non-polar molecules are there. Okay, here, and they are bound by this process. What is called as the van der Waals process? P process. So here, you know the examples: hydrogen, okay, or some nitrogen, or some oxygen, or chlorine, etc., or chlorine, okay, or some alkynes, alkenes, alkynes, okay, or some the phosphorus molecules or sulfur molecules or some iodine molecules, etc. Okay. Now in this case, if you consider one of the example, suppose some normal alkane, okay, or some normal N, say pentane, or some neopentane. Okay. So this has a straight chain, and this is a compact. This is a compact, and because of this compact nature, the less bonds bonding here. Okay, less these forces, less bonding internally. Therefore, low melting points. This has higher than this. Okay, than this. Example, your or yeah. Okay. So here, the non-polar molecules. In the case of non-polar molecules, in molecular solids. Now, what types of the questions are there? Generally, you have given such an example: HCl, SO2, SO3, or these examples. Okay, alkanes, alkenes. Okay, and or in these examples, and you have to classify all these substances according to the molecular solids, whether ionic solids or the metallic solids or coherent solids. Okay, these examples are also important. Now consider the ionic types of the solids. Ionic types of the solids. Second. Now what is the ionic solids? Second. Ionic solids. As per discussed, there are positive cations and negative anions. They are arranged systematically. For example, okay, what are the binding force? The ionic bonds. It is a stronger bond. Strongest one. A strong. Strong. Okay. So here, directional, non-directional character ionic bonds, they are present there, and in this case they are tightly bound. No free ions. Therefore, they are generally non-conducting. Okay, but becomes conducting in molten or fused at high temperature when they melt, or in aqueous solution, because ionic salts are soluble in polar solvents like water. Forms of three ions, and then they are conducting, but in solid states they are non-conducting. Okay, non-conducting means of course in solid state. Okay, and all valencies is very important. Okay, all valencies, all charges are satisfied. Okay, fulfill. Satisfied means fulfill. Satisfied. Therefore, they are non-conducting. Okay, all charges are fulfilled. They are satisfied, and they are therefore brittle also. Brittle. That is when some external stress is applied, then applied stress gave charge. Okay, they get it. So this is a very important property. But opposite of ionic solids, the metallic solids are there. where the atoms are the repeating units and metallic bonds. Metallic bond. That is the bond between. What is metallic bonds? Let us consider. So diagram of this. Here, metallic salts. As you know, the repeating units are the metal atoms. Okay, these are the repeating units, and the binding forces are the metallic bonds. Or between positively charged atom nucleus called as kernels. And mobile, that is valence. Okay, 3 electrons. That means if you consider it's a C model, okay, example is explained by C atomic model. Okay, so according to this model, there is a fixed structure arrangement of the atoms, and these are the atoms. And the mobile electrons, they are the positively charged nucleus is there, the nuclear charge is stable, and the outermost valence electrons, they are delocalized here, negative charge. Okay, negative charge is there. In a C. Okay. So depending upon this number of electrons, in a sea of electrons, this make backbone. Okay. So here the stable and fixed kernels are fixed. Kernels are fixed. Fixed. Okay. And the electrons are said to be electrons are mobile. So here one kernel layer can be slide. Okay. One kernel layer can slide over other. Therefore, interest, the metals are malleable and ductile. also. So it can be made of 5 sheet of metal or 5 wire of the metal can be drawn, because there is a flexibility. One layer if disturbed, or these electrons can be take any positions. Okay, they are mobile one. Okay, so sliding can be possible. Okay, so here these are number of metals. All metals are the examples here. Now consider the fourth point, that is the coherent or gain, as known as network studies. For example, if you consider, so here you know the atoms of the non-metals. For example, carbon or sulfur, they forms different their compounds. But if there is a network, so what is important? Due to the network of covalent bonds, these compounds becomes very strong. Okay, very strong bonding bond, and therefore they are high. Okay, they become very high. Okay, for example, you know diamond, very important. Already discussed here. Okay, or some silica or silicon. Okay, silicon or some silica sand. Okay, or some aluminium nitride. Okay, there is a network of the bonds, and because of this network of the covalent bond, even though covalent bond is weaker than the ionic bond, but because of the network, the compounds, these molecules, they form a very stronger bonds than the ionic bonds also, ionic compounds also. Okay, therefore here they have a high melting point. For example, you know, for a diamond has 3550 degrees Celsius is the melting point. Okay, so here on the basis of the binding force for different repeating units, crystalline substances are classified, and so the examples are important also. On the basis of these repeating units and binding forces, you must be able to classify the given examples. Okay. Hello friends, we are going to study the next point, and which is very important. Okay, that is for space letters. As you know, in a crystalline type of the solids, the arrangement is long-term and ordered arrangement. Okay, so here if you consider the arrangement of some, hypothetically, these are suppose anions. Anions are larger ions, larger particles. Take a main set, forms main backbones, larger in size, anions, and maybe there some vacant space is there. Those are known as the voids. Those are suppose smaller ions are there. Smaller ions are there, or smaller particles are there. So here the particular arrangement gives a crystal lattice. Okay. Now every time it is not possible to denote all these big spherical shaped atoms like this. Okay, like this. Okay, so these are the spherical shaped what atoms, ions or molecules. All are the atoms or ions. They are spherical in shape. So here they are denoted by the dot. Dot. Okay. So what it means? So here we are going to define first space lattice. What is this? So here there is a regular arrangement of the particles in three dimensions. Okay. So here we can write here regular, definite, okay, arrangement of particles in three-dimensional 3D three-dimension is in crystal is formed. Okay, so here in crystal, how they are shown this arrangement by the help of lattice points. Okay, so in crystal, this three-dimensional arrangement, or it may be shown by lattice points. Lattice points. Okay, is called as the space lattice. Called as space lattice. What it means? So like this. So here the cations. Okay, sometimes the cations. Okay, cations or some anions. Anions. These are anions are bigger in size. Okay, so here anions. Dot. Okay. Now we can also written as the lattice points. Lattice points. Okay. So here the relative positions of particles in crystal is shown by dot. X dot are called as lattice points. Okay. Now very important thing is there, because of this regular arrangement and definite arrangement, definite shaped unit cells, smallest fundamental building units. Okay, so this is a smallest some unit cells are formed. Unit cell. What are unit cells? Very important. So here one can define smallest but definite. Structural unit cells. Or structural units are called as unit cells. Okay. So what are unit cells? So those are the smallest but definite structural building units in crystalline substance. Okay. A crystal lattice is known as lattice. So here, smallest but definite. So arrangement is a particular arrangement is there, and such a repeating units are there. Structural. One can also recognize a structural repeating unit. Repeating unit. Okay. So here, repeating, definite, and smallest building units. Which so here the very important character, the shape of star is same as the shape of its unit shape. Okay, its unit. So in this case, how many possibilities are the shapes of different unit shapes? And according to these shapes, there are about 14 types of the unit cells are there. Unit cells, and they are known as various lattices. Okay, so every unit cell is characterized by all these unit cells are characterized by two things. First, the edge plane, and second, edge angle. Okay, and each unit cell can study by explain. Okay. Explain according to their angles. Those are known as alpha, beta, gamma. Okay, we are going to study what are alpha, what are beta, and what are gamma. Second, edges shown by A, B, C along 3 dimensions. X, Y, and Z axes are there in 3 dimensions. Similarly, corners or some faces, etc. One by one. Okay, this is not important, but then now we are going to study about the 14 types of unit cells. Here, these are the very important point. The various faces, 14 unit cells are there. What type of this? For example, suppose this is the one of the unit cell. This is known as a cubic unit cell. Okay, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 corners, 8 vertices are there. And how many faces are there? 1, 2, 3, 4, 5, 6. 6 faces are there. Okay, how many edges are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 edges are there. Okay. Now what is the body part? So this is the body part. Interior, inside of this body part. Okay. So in a cubic cell, therefore there are 8 vertices, 6 faces, and how many? 12 edges and 1 body center. Only one. Every unit cell has a one body center. Now, in this case, how many particles are arranged? The particles are arranged, or particles are arranged, and then that's why this type of the cell is formed. And such a 14 types of unit cells are formed. So this is the one of the one cubic cell. Similarly, one more unit cell is there. Now, in this case, if you consider at this bottom there is a hexagon 1, 2, 3, 4, 5, 6. Similarly, there is a one hexagon 1, 2, 3, 4, 5, 6. Okay, so there is 6 angles. Here also 6 angles, and here there are 6 faces. There are also 6 edges. Okay, 6 edges, not a faces. So here in this case, 1, 2, 3, 4, 5, 6 edges, 7, 8, 9, 10, 11, 12 edges, 13, 14, 15, 16, 17, 18. Okay, so there are total 18 such edges. How many corners are there? 1, 2, 3, 4, 5, 6 corners, and 7, 8, 9, 10, 11, 12. 12 corners are there. Okay, so we are going to study in details only about the cubic cell and hexagonal. This is the hexagonal type of unit cell. This is the cubic type of the unit cells. And again, there is variation. If you press this, the angle changes, not remains 90 degree, or this side, or this side, or this side, any side. Now, how the angles are represented by the letters alpha, beta, gamma. Okay, which is one is the alpha, which one is the beta, and which one is the gamma in this case, as well as in this case also. We are going to study here in details. Now, yet you come to know about the space lattice, that is the here regular and definite arrangement of the particles in 3-dimensional. It is called as a unit crystal lattice, called as space lattice. Okay, or it is nothing but a crystal structure, crystal lattice. Okay, and here all the relative positions, they are relative positions of the atoms or ions or molecules. That means here this and this relative, these are the relative positions. Here at each corner, particular angle is there, particular distance is there, particular distance is there, particular angle is there. So they are denoted by lattice points. Okay, the relative positions of the points, these atoms or molecules, and the unit cell. So we are going to study about the Hsc S.S.Takalkar. 14 types of the unit cells are there. So what are those 14 types? Let us study one by one. Then let us consider 14 types. There are actually 7 Hsc lattice. What it means? It is nothing but the different types of unit cells. 14 types of unit cells are known as Hsc lattices. Okay. So here there are actually 7 systems, and it gives 14 types of unit cells. What are those? Let us, I am going to write here. Here, let us consider types or systems. Okay. So here different systems are there. Then types. characterized by alpha, beta, gamma, and again the angle made by them as well as ABC, or one can write here first A, B and C, alpha, beta, gamma. Okay. So what does it mean? Now consider here, this is the one of the cubic cell. I am going to draw here a cube. Back side. Okay. Now here, if there is a at each corner there is a particle. It may be an atom or it may be an ion. Generally, the bigger size anions occupy the main positions. Okay. Now this is the cubic one. Okay, like this. Now, see, if you consider this axis here, back side, or this front side, above the plane, and this in plane, but this side. So one can here draw the coordinates. This is suppose z axis. This is suppose x axis, y axis. Or any you can do it. Okay. Okay. Suppose this is the x, this is the y. Okay. Now above the plane. So here it is denoted by A, letter A, and this length is denoted by B. It may be same or may not be same. Okay. And this is the length denoted by C. Similarly, this angle. Okay. So these are the A, B, C. These are the alpha. This is a beta, and this angle is said to be a gamma. Okay. So alpha is the angle made by y and z lengths. Okay, B and C. Again, this C and A makes a beta angle, and A and B makes a gamma angle. Okay. Consider. So suppose this is the one. So here one can consider. So this is a B. Okay. This is a C, and this is above the plane. That is A. Okay. Or this is the angle. Okay. This is alpha. Okay. And this is in plane. This is the gamma, and in this plane this is the beta. Okay. So here one can represent like this. Okay. Then friends, this is for the cubic one, where all the edge lengths are same and all the angles are 90. Okay. But if you consider another type of the cell here, so this is the hexagon. Okay. In one plane. So this angle gamma and all above angles they are 90 degree. 90. Okay. 90. 90. Okay. This is 120 degree. Okay. This gamma angles. So these are the alpha is 90, beta is 90. But this gamma is equal to 120 in one plane. So this is a 120, but this is a 90 degree. This is a 90 degree, and in plane here it is in between A. Okay, like this. Okay, so this is the suppose x-axis. This is say y-axis, and here it is a z-axis. Okay, this is suppose y-axis. So here the angle made by this x and y is said to be a gamma angle. Okay, this y and this is the x, this gamma angle. So in plane, this is the gamma angle. Okay, and it is 120. This is of course 90, and this is also 90. Okay, we are going to study similar fashion different types of the dimension first. Okay. Now, first is cubic. Cubic. Okay. Second, rhomboid. Okay. Trigonal, also known as the rhomboid. Rhomboid. Okay, this is important. Or rhomboid. I am writing here hexagonal, monoclinic, and last that is a triclinic. Okay, there are 7 systems. 1. Okay, so I am here. It is a quite bigger system. So here tetragonal, tetra, shifted, second, orthorhombic, third, okay, here, fourth, trigonal or rhombohedral, hexagonal, monoclinic, yeah, and triclinic. Okay, so there are 7 systems. Okay, now here, as discussed here, what are the ABC? All A and B are same. A is equal to B is equal to C. All the edge lengths are same. A, B, C. Okay, here. Similarly, alpha, beta, gamma, or alpha is similar to beta, is similar to gamma, and all are 90 degrees. All 90 degrees. Okay. Now, what is about the tetragonal? Tetragonal, there is one example. Here, I am going to write here. So here, the only A is equal to B, but the C is not different. Some another type, A and B are same. Okay, A and B are same. A and B are same, but one is different. This and this are same, but this is not the same. So here, this A or this B, okay, yeah, they are same, but this is quite different. Okay, you consider this and this are same, okay, but this is different. And if you consider now the orthorhombic, where consider A is not equal to B, is not equal to C. So this is the example of matchbox. So this is the matchbox. Well-known example. Here, all the A, B, C are not same. A is different than B, B is different than C. All the differences are there. Okay, this is the orthorhombic system. Now, rhombohedral, these are repeated again. Oh, so here, first write all these characteristics. Again, this is repeated. A is equal to B is not equal to C. Because in exam, they will always ask what are the ABC and alpha beta characteristics of all these systems. Okay, and again this A is not equal to B is not equal to C, and I will again repeat this one. A is not equal to B is not equal to C. Then, in the case of alpha beta, this field set, all angles are same here. Okay, here are, and after this, the angle going to change. Angle changes. Okay, yeah. In a rhombohedral type of the shape, because in this case This is a very important hexagonal type of the cell. We are going to study in details, as well as cubic type of the cells. We are going to study in details. This is a cubic cell and this is a hexagonal cell. Here, this angle already discussed, it is a 120. So here, okay. So what is that? Alpha and beta are. Okay. What are those? Which one is alpha? So alpha, this and this beta are of course 90 degree, and but gamma is equal to 120. So this is about the hexagonal type of the cell. Okay. Now in this case, the rhombohedral one, the alpha and beta and gamma, they are same, but all they are not other than 90 degree. Okay, alpha, beta, gamma, these angles are same, but they are other than 90 degree. So dear friends, you keep in mind this one, then others are easy. Now consider one by one. Cubic cell. There are actually three types. 1, 2, 3. Okay. Okay. Here, tetragonal. There are again 2 types. There are 4 types. 1, 2, 3, 4. There are 2 types. Okay, 2 types. 1, 2, 3 types. Okay. Okay. There is only 1 type. Hexagonal is only 1 type. Monoclinic, there is again 2 types. 2 types. And it is what those types are. Okay. Oh. So in this case, monoclinic and triclinic. This is a very interesting set. Alpha is not equal to beta, is not equal to gamma, is not equal to 90 degree. All the angles are not same, and again they are not other than 90 degrees. Okay. Similarly, all the edges are also different. Okay. In this case, here for this is very important thing, that is alpha and gamma are same, and it is 90 degree. But beta is other than 90 degree. Okay, that means suppose this is the one of the cell, and if you twist, okay, I will show here. Yeah. So here alpha and gamma are same. So this is 90 degree. This is 90 degree. Okay, they are 90 degree. But this angle, beta angle, the angle between the z and this x-axis. So this angle, okay, this angle is not 90 degree. That means this cell can be twist like this. Okay, twist. Consider this twisting of this. So this is nothing but the here this remains 90 degree, but because of this twisting in this plane, okay, consider this. This angle changes. This angle changes. Okay. So here the gamma is other than 90 degree. It may be a this one or this one, anyone, not 90 degree. So here again we are going to show the different types of cubic cell. Consider this cubic cell. What is the characters of the ABC and of the beta? Of course, all the lanes are same. This is the B, this is the A, B, and this is the C. Okay. So the alpha, beta, and gamma, they are 90 degree. Now, in a simple cell, there are 8 ions or molecules, atoms are at 8 corners. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. And this is called as a simple cubic cell or primitive simple. Okay, simple or primitive cubic cell. Now, along with this, there are 8 balls at 8 corners, and there is one more ball at the center here. At the center, there is one more ball. Okay, one more particle. So here, we consider this cell diagrammatically. Consider. one more type set. Okay, consider that one by one. So here there are 8 ions, particles at 8 corners. This is a simple cubic or primitive cubic set. Now here there are, of course, as usual, 8 atoms or ions at the 8 corners everywhere. 1, 2, 3, 4, 5, 6, 7, 8. Now, what is the difference? In this case, here it is a simple cubic cell where 8 atoms or ions are at the 8 corners or 8 vertices of the cubic cell, and in addition, at the center there is a one more. Okay, so this is called as a body center cubic cell. Here, instead of body, there are 6 faces. As you know, here 1, 2, 3, 4, 5 above and below 6 faces are there. So here, at the center of each face, 1, 2. So this is the one face. Okay. Back side. This is a side and this side. Bottom side. So again, there are 1 ion at the center of each face, and this is called as a face center cubic cell. Okay. So here, depending upon this type, there are simple body and face. Okay. So this is also known as a BCC, body centered cubic cell, and FCC, head centered cubic cell. We are going to denote it by the BCC or HC approximation, and simple cubic cell. Now in this case, tetragonal, there are only at the face, okay, or body center. There are 2 types. One is the simple tetragonal cell, and here body tetragonal cell. Here again, orthorhombic. This is a very famous example of the matchbox where the ABC all are different and all the angles are still 90 degrees. Okay. So here it remains as it is. Only here is the simple. Okay. Here is the body. Then here is a face, and one more is the end and centered. Okay, centered orthorhombic unit set. Okay, simple body. Perfect. That means if you consider different dimensions here, we can write. Now consider the rhombohedral cells. There is only one simple. This is also simple. Monoclinic here and center and simple. Okay. So end center means what? Suppose this is the one of the cell. Imagine this is actually a cubic cell where A, B, C are same, alpha, beta, gamma are 90 degree, but only opposite face. Here and here, at the face of opposite these faces, there is a one more atoms or ions. Okay. So here, one can write here for ion centered type, there are ion or particles, atoms at opposite faces. Only of course 2 opposite faces. here one can write only two opposite faces has one each atom or ions, whatever. Now consider very typical examples. These are the diamond. We are going to study in details because you already know diamond has a sp3 hybridization. This carbon is linked with net 1 or some polonium metal, or some Cesium chloride, sodium chloride, or some kind N2S, etc. Okay. Or in a hexagonal, this is the important because we are going to study details, the height. Okay. And these are all the examples. We are going to study here unit cells in details.
Oh, sorry. Slowly but really something there.
Now count here. Dear friends, as you count here, there are 14 types of the, of course, unit cells called as the Polarities. We are going to stop here. Okay, thank you.